Okay, welcome back, and let us solve a problem for the entropy. So basically here we have a heat pump system where we have the different components, the compressor, the condenser, an expansion valve, and an evaporator, and we have all the different conditions all over here. So this is refrigerant that goes from 1, goes to the compressors 2, then goes to a condenser 2.3, goes through a valve, and the cycles restart again. And then on this side you have the air that extracts the heat from so that's why it's a heat pump. It removes the heat over here. Okay, so you see the air comes at 20 but leaves at 50, and that process is a constant bar at constant pressure. And basically what we need to do is to draw the TS diagram for the refrigerant. So basically 1, 2, 3, 4, and find out what is the change of entropy into the compressor, into the condenser, and in the expansion valve. All right, so let's start with this problem. The first thing we need to do is to do the TS diagram. So in order to do the TS diagram, we need to find what is the state at 1, 2, 3, and 4. Okay. So we know the substance is the substance is refrigerant 322, and we know the states at 1 because we know two properties. We know P1 and T1. Here we know P2 and T2. So we can find what is the state. All right, so let's do that first. So let's say here in part A, we're going to do the TS diagram. Okay, so just by looking at the figure here we see we have 3.5 bars, and here we have 14 bars. So when the refrigerant goes to the compressor, it gets compressed from 3.5 to 14. So maybe on this figure what we can do is lines of constant pressure. This way, where this would be P1 equal 3.5 and P2 equal to 14 bar. So in order to know the states, at T1 we know the temperature. So in order to know the state, which is minus 5 degrees Celsius. So in order to know the state, we need to find what is the saturation temperature over here. Let's say T saturation over here. And that we can get that information from table, let's see. Table A8 that I have over here. So let me write it down. So from table A8, which is for the refrigerant, the tables are attached. So let me see if I can zoom in a little bit. So let's see, for 3.5, which is right here, what is the temperature? Minus 10.39. So we go to the figure, this would be minus 10.39. And we are minus 5, so minus 5 is hotter than minus 10.39. So that means that state 1 should be somewhere over here. Okay, so from table A8, at P equal 3.5 bars, we know that T saturation is equal to minus 10.39. Okay, since T1 is higher than the T saturation, state 1 is superheated, or basically gas. Okay, so we might need more properties. So let's find what would be the values. So we might need H1. So that means we need to go to the superheated tables. So H1 and S1. So this time we go to table A9, and we need to know two things: at P equals 3.5 and T equal to -5 degrees Celsius. So I have the table right here. So let's see, you can read. So here 3.5 at -5. We have H to be equal to 249.75 and S equal to 0.9572. So we can write this down. So H1 is equal to 249.75. Not sure we're going to need this quantity, but it's better to have more than not sufficient information. So now for state 2, we can basically do the same thing from table A8 at P equal this time what? 14 bars. We know that the T saturation is equal to what? So let me go back to table A8 at 14 is down here, is equal to 36.29. Celsius. And what is T2? 75. So T2 higher than T saturation. So what does that mean? That we are still on the superheated area. Okay, now let's find out if we are going to the right or to the left of the one. So since it's superheated, we need to go now back to table A9, but this time at 14. So this would be table A9 at 14 and 75. So here we don't have the value 75, but we have the 70 and 80. So we can just add the value at 70, the value at 80, and divide by 2, and it should give you 75. So we can do that for H. So it would be 290.01 plus 298.34 divided by 2. And for the enthalpy, 0.9703 plus 0.9942 divided by 2. Okay, so let's do that. So at 1475, we're going to have what? H2 will be equal to 290.01 plus 298.34 divided by 2, which gives us 294.175, and S2 will be equal to what? 0.9703 plus 0.9942 divided by 2, and this gives us that is equal to 0.98225. So let's maybe try to mark these values because we might need them later on. Okay, and we can see what that S2 actually is 0.98, S1 was 0.95. So what does that mean for the figure? Is that we're going to go, let's say, to a point over here. So that means we go from here to here. And this will be Okay. All right, now let's go for state 3. Let me zoom out so you can see everything. So again, for state 3, we need to know two properties in order to define the state. So where is the statement? Is right here. So we have two properties at point 3? Yes, we know P3 and T3. So let's say at P3 equal 14 bars and T3 equal 28 degrees Celsius. So we can do the same thing. We can go to table A8, and actually we already have some of that information, because what does that mean on the figure? This is the 14, so that means that whatever happens at constant pressure, so we're going to move along this line over here. So this is 28, and the saturation at 14 was 36. T saturation equal to 36.29. Okay, so what does that mean about point 3? It's lower, it's 28, so let's say point 3 will be somewhere over here. So over here we go from superheated, so that means we are going through the condenser. So throughout the condenser, the refrigerant goes from superheated, becomes a mixture, and ends up being a liquid. So that one is a little bit more complicated, because if you remember, we don't have tables for saturated liquids in this area, but we say that the properties do not change much in function of the pressure. So we only need to, in order to find the value of the property, we only need to consider the temperature. So that means that we need to go to table A7. So what is table A7? Table A7, let's see if I find it. It's basically the properties of saturated refrigerant. Okay, and we look at the temperature, and we are lucky because we have the value 28 right here. So let me zoom in. Negative 28. So we say negative 28. We know then that S3 will be equal to what? S fluid, which is right here. So it should be what? Is it 28 or minus 28? Hold on 1 second. Is 28. So sorry, we are all the way down. 28. So S fluid is 0.2936, and H3 will be H fluid, 279.05. So zoom out again. So from table A7, at T equal 28 degrees Celsius, you're gonna have that S3 to be equal to S fluid at 28 equal to 0.2936, and H3 equal to H fluid equal to 79.05. Okay. All right, so we have one more. Let's find out what is 3. So this is our page 1. Okay, so now we are here over the expansion valve. So in order to find the state at 4, remember we always need to know two things. But what happens when you go through an expansion valve? We know that H4 should be equal to H3. So at state 4, we know basically two things. We know that P4 is 3.5 bars, and we know that H4 will be equal to H3, which is equal to 79.05. So we know two things. But if we look at the figure again, means that we need to be somewhere along this line of constant pressure of 3.5. So let's go now to table A8 at P equals 3.5 bars and find out at 3.5 bars. That means we are right here. This is H fluid, this is H gas. So H fluid is 33.09, H gas is 246.00. So we have H gas, we have that H fluid, H gas. So H fluid is 33.09 and H gas is 246. And similarly, probably we can do it now. S fluid is equal to 0.1328 and S gas is 0.9431. So we are along this line, 0.1328, 0.9431. Zero 0.1328 and gas equal to 0.9431. Okay, so what do we find out over here? We see that H4, which is 79.05, is between H fluid and H gas. So what does that mean? Is that at state 4, the substance is a mixture. So we come to this figure. 4, let's say, will be somewhere over here. So basically we have 1, 2, 3, 4, and now this go back to 1 over here. Okay, so now we go from a mixture, and it's going to become a superheated gas again after going through the evaporator. Alright, but since it's a mixture, we need to find what is the quality factor. So what can we do in order to find the quality factor? So we know the enthalpy, so we know that H4 will be equal to H fluid plus X4 H gas minus H fluid. So from here we can solve for X4 will be equal to H4 minus H fluid divided by H gas minus H fluid. So if we do the numerical application, let's see what we get for X4 will be equal to what? 79.05 minus H fluid is 33.09 divided by 246 minus 33.09. And if you do this calculation, you get 0.216, which means what? 21.6% is in the gas state. So basically in this figure, 21.6% of the refrigerant is under gas state, the rest is under liquid state. That's why it's kind of closer to this line. Okay, so now that we know the quality factor, using the same equation as this one, but for the entropy, we can find that the entropy will be equal to what? S fluid plus X4 S gas minus S fluid. So S4, we have the data right here, will be equal to what? 0.1328 plus 0.216 times 0.9431 minus 0.1328. And if you do this calculation, you get that S4 is equal to 0.3078. Okay, and we know also H4, which is equal to H3. So if needed, we know this over here. Okay. So why are we doing all this stuff? If you remember, part A is to do the TDS relation, which we just finished, but we need to find what is the entropy production in the condenser, the compressor, and the expansion valve. So basically, we need to know S1, S2, S3, S4, okay? Which we know, but we also need to find S5 and X6. So let's do that. Okay, so we need to find S5, S6. So remember, this is for the air. So we are talking here about the air that is going from T5 20 degrees at 1 bar to T6 equal 50 at 1 bar as well. So let's maybe do the figure over here. 5, 6, T5 equal 20, P5 equal 1, T6 equal 50, P6 equal 1. So on the problem, they tell us to assume the air as an ideal gas. So if it is an ideal gas, it's also an ideal substance. But basically, ideal gas always means that we could use the ideal gas relation equal PV equal RT. All right, but here we need to use the TDS relation, but I don't like to do engineering like cooking when you go and find just one equation. I think it's better to kind of rederive it in the fastest way. So what do we learn is that the first principle of thermodynamics is equal to Q minus D minus work equals to du if we neglect the kinetic and potential energy. Now this is also equal to, so where W here is equal to P dV. So we have Q is equal to du plus P dV. Okay, so basically this is, if you remember, okay, so we have this equation here. And then if you define H as being equal u plus pv, you find out that the total derivative dh is equal to du plus p dv minus v dp. So if you substitute this dh, you rewrite the du over here, so basically this will mean that du is equal to what? dh minus p dv minus v dp. So if I substitute this equation in here, what do you get? Q will be equal to dH minus V dP. But in this problem, what do we know? Pressure is constant, so that means that dP will be 0. So basically this means that just Q will be equal to dH. Okay? And for an ideal gas, this will be equal to what? M Cp dt. In this case, this is a mass flow, so we need to talk about a mass flow here. And then this becomes really the heat transfer. Okay, but that's not the important part. So we have this part. Then, using the definition for entropy, what do we have? ds is equal to delta Q over T. So that means that delta Q is equal to T ds. And remember that this is approximately equal to Q, which means what? I can substitute into this equation, so I get T ds. This is just redoing the derivation of the T ds relation. Simplify would be equal in this case M Cp dt. So now going very quick, if I divide by T on both sides, what do I get? ds equal to M Cp dt over T. Next, I'm going to integrate. So what do I get here? ds equal to M is constant, Cp is also constant, dt over T, and here we're integrating what are the limits? S5, S6, T5, T6. So that will mean over here that the change in entropy, S6 minus S5, will be equal to what? Mass flow of air times Cp log T6 over T5. Okay, so we need to find what is the mass flow of air. So what is the definition of mass flow? Is volumetric flow rate divided by specific volume. So over here in this problem is given to us the volumetric flow rate at 5 over here. So we can say that the mass flow of air is equal to AV5 divided by V5. And we can use the ideal gas relation, which is PV equal RT, to find V. So V will be equal to RT divided by P. So basically at the end we have that the mass flow will be equal to AV5, which is given, divided by RT5 divided by P5. Okay, so let's see what is R over here. So R in this equation is the universal gas constant divided by the molar mass. So this will be equal to 8.314, and the density of air is 28.97. Okay, then T5, we know that T5 is 50 degrees Celsius, but we need to transform that temperature into Kelvin, so that will be 323 Kelvin. And P5 is what? 1 bar, which is 100 kilopascals. So if we do the substitutions, so let us go to the next page to do the substitutions. We are going to get that mass flow of air is equal to what? AV5 in the problem was given to be equal to 0.42 divided by 8.314 divided by 28.97 times T5. So let's see, here I did a mistake, so let me go back and just find out. Because T5, sorry for that, T5 is not 50 but 20 degrees Celsius, so this should be really 293. Okay, if I show you here on the figure, T5 is 20 and T6 is the one that was 50, so an AV is 0.42. Sorry for that. So times 293, and now this will be what? Divided by 100 kilopascals. So if you do this calculation, you get that the mass flow of air is going to be equal to 0.499 kilograms per second. Okay, so that means that now we know everything about to find what is the change of entropy for the air. But let's find out what will be the change of entropy for the refrigerant. So the same way we need to know the mass flow for the air in order to find out the total change in entropy for the air, we need to do one for the refrigerant. So in order to do that, we're going to consider the control volume of the condenser, where we have both of us, okay? And we can write down the first principle of thermodynamics for a control volume. So basically now our goal is to find the mass flow of refrigerant. So in order to do that, we're going to consider the condenser, where we have both fluids. So this is the condenser that we consider to be our control volume. We know this is divided by 2. So on top we have the air, which we know everything now, and we have here 5, we have here 6. Okay, we know this air. And then at the bottom we have the refrigerant that goes this way, where this is 2 and this is 3. Okay, so this is the control volume. So neglecting kinetic and potential energy, the first principle of thermodynamics here can be written as what? Q dot minus power. Now we look at whatever is going in. So we have M of refrigerant times H2 plus mass flow of air times H5. Now we see what's coming out. Mass flow of refrigerant H3, and the air coming out is M air H6. So as you can see on the figure, there is no heat or work. So we can rewrite M mass flow of the refrigerant, let's say H2 minus H3, is equal to the mass flow of air H6 minus H5, which means that from here we can find out that the mass flow of the refrigerant to be equal to the mass flow of air H6 minus H5 divided by H2 minus H3. So now remember that for an ideal gas, dH, so H6 minus H5 is more or less proportional to what? Cp T6 minus T5. This comes from the fact that dH equal Cp delta T. Okay? We have covered this multiple times on previous videos. So we can rewrite that the mass flow for the refrigerant can be written as mass flow of air Cp T6 minus T5 divided by H2 minus H3, which we have. And we have the mass flow of air. So all we need over here is to find what is Cp. So the value for Cp, we can find it from table 820. So here you have Cp for air at different temperatures. You see it's almost equal to 1, so you don't really need to interpolate it. The difference is very small, it's just on the third decimal, so I'm just going to consider the value at 300. So at 300, Cp is equal to 1.005 for air. So I can write down over here, table 820, at T equal 300 Kelvin, Cp is equal to 1.005. Okay, and the units are actually kilojoules per kilogram Kelvin. Okay, so let's do the numerical application for this one over here. So if we do numerical application, we're going to have the mass flow of refrigerant is equal to the mass flow of air, Cp T6 minus T5 divided by H2 minus H3. So this is equal to what? Mass flow of air we find out to be equal to 0.499 times 1.005 T6 is 50 minus 25. Let's double check these values. Yeah. Divided by H2. We need to go back to our pages. So H2 is equal to what? So I have H3 to be equal to 79.05. And let's even find H2 294.175. Okay, so if you do this calculation, we get that the mass flow of the refrigerant is equal to 0.07 kilograms per second. Okay, so finally we have all the information that we need in order to find out the change of entropy on each one of the components. So let's find out first the condenser. No, let's start by the compressor. So if you do the figure of the compressor, one, two. So this is our control volume. So recalling the principle of increasing entropy of the universe, the total change of entropy will be equal to the change of entropy of the system plus the change of entropy with the surrounding. So in this case, there is no heat going out, so this is 0. And this will be equal to what? Mass flow of the refrigerant, let's call it this way, times what? S2 minus S1. So we do this calculation, where do you get? Delta S for the compressor will be equal to mass flow of the refrigerant is 0.07. S2 we find out to be equal to 0.98225 minus 0.9572. So that gives us that for the compressor, the change in entropy is equal to 1.75 10 to the minus 3 kilojoules per degree Kelvin. So that means this is the amount of energy that is wasted or not used by compressing the refrigerant. Now let's look at the throttling device or the valve. So when we look at the valve, we are over here. Three and 4. Again, this should be our control volume. And we have the mass flow of refrigerant. Basically, it's identical what we are doing. So the total change of entropy is equal to the change of entropy of the system plus the change of entropy with the surrounding. Since there is not heat transfer, this is 0, and this becomes what? M dot refrigerant S4 minus S3, which should give you that the change of entropy in the valve is equal to what? 0.07 times 0.3078 minus 0.2936, which gives you that the change of entropy throughout the valve is equal to 9.94 10 to the minus 4 kilojoules per kilogram. Okay, and there's a reason why I leave the condenser at the end, because it's the element where we have both fluids, the air and the refrigerant. Okay, so for the condenser, again, let's do a quick figure. We have at the top the air, going between 5 and 6. This is mass flow of air. And then at the bottom we have the refrigerant, and that states 2 and 3. And refrigerant. In this case, this will be our control volume. Okay, so for that control volume, again, the change in entropy is equal to the change of entropy of the system plus the change of entropy with the surrounding. Since there is no heat transfer, this will be equal to 0. But now is when it's a little bit different. This will be equal to what? To the mass flow of air times what? S6 minus S5 plus the mass flow of refrigerant times S3 minus S2. But in the previous pages, in one of the previous pages, we find out that, let's see, so all this term over here, really this is this is CPL T6 over T5. So we can write this as M air Cp log T6 over T5 plus M refrigerant S3 minus S2. So if we do the calculation, the total change in entropy should be equal to what? So let's see, what was the change in mass flow for air is 0.499 times Cp is 1.005. Log of 50 would be 323 divided by 293. Plus the mass flow of refrigerant is equal to what? 0.07 times S3 is 0. I need to go check that value. 0.2936 minus S2 is 0.98225. So you see this value will be negative, but which is fine. Okay, we'll see what is the meaning of that. So if you do the calculation, all this term here will be equal to 0.98225 0.0488, and this term here is equal to negative 0.0480. So basically what does that mean? Is that the air increases the temperature. We know it goes from what, 20 to 50, so it's gaining energy. That's why it's positive. The refrigerant is going from one temperature. It's going from T2 was equal to 75 degrees Celsius to T3 78. So basically it's losing energy, so that's why it's negative. So at the end, the total change you will see is very, very small. It's equal to what? 0.0008 kilojoules per degree Kelvin. And this is, in order to be correct, you see this value can be equal to 0 or positive, but this one can never be negative. Of one of the process, yes, can be negative, but the overall can never be negative. It needs to be equal to 0 or higher than 0 because of the principle of increasing entropy of the universe. So again, this would be the value for the compressor. And when it's positive, means that it's irreversible. So each one of the components is losing some entropy. So this was a long problem, but if you know how to do this one, you have the knowledge to move to now more advanced material. Thank you for your attention.